Least squares prediction. Frequently, we wish to forecast into the future. For example, if you run a cafe, you might wish to forecast the number of customers that will visit your shop, say next week. If you're making decisions on whether to invest in the stock of a company, certainly now you might want to forecast the future profits of this company. Utilizing our OLS regression results, we can actually do such a forecasting. So recall that we have a simple linear regression model of this, and under the assumptions SR1 to SR6, and we developed estimators for beta 1 and beta 2. These are called OLS estimator. B1 is the estimator of beta 1, B2 is the estimator of beta 2, and they are blue-based, linear, unbiased estimators. The B1 and B2, they are random variable, normally distributed. Now suppose we know in the future X will take a value of X0. For example, in our food consumption expenditure models, our X is income. So maybe in the next year the income is $2,000 weekly, which means X0 will be 20. Then we know that the associated Y, food consumption expenditure, is Y0, and which is not known to us. So we want to forecast this Y0. So we want to predict Y0. We know that Y0 is equal to beta 1, which is beta 1, which is not random variable, is a constant, okay, unknown to us. Beta 1 plus beta 2 times X0. Note that we know X0. We know that the X0 will take 20 plus E0, which is random errors. So this E0 is a random component of Y0, and this part is the systematic non-random part, and actually is the conditional, is the expectation of Y0 conditional X0, which is B1 plus B2 times X0. The only problem here is that we don't know beta 1 and beta 2 what they are. So we can estimate. Fortunately, we can estimate beta 1, beta 2. So we plug which is B1 and B2. We plug them into that equation, and we get an estimate of this systematic non-random part. And for the random component, we can also kind of estimate it by its expected value, which is just zero. So now we have a prediction of Y0, an estimate of this Y0. So our prediction of Y0 is the estimate of the non-random part plus the estimate of the random part, which is simply equal to B1 plus B2 times X0. And we call this least squares predictor. And know that this X0, Y hat 0 is actually on the regression line. It comes from our regression directly. And this Y hat 0 itself is a random variable because B1 and B2 themselves are random variables. and actually it is normally distributed. So we find a predictor of Y0, and this is an individual predictions. So how now the next question is, how well does our least squares predictor perform? We want to make sure that our prediction is reasonably well in a sense, right? Okay, to answer these questions, let us define forecast error called F, which is the difference of Y0, the true unobserved value of Y, given that X is equal to X0, and the random component is E0. And our predictions. We know that Y0 is equal to this, beta 1 plus beta 2, X0 plus E0. Our predictor is B1 plus B2 X0. So we can manipulate them to get this equation. Beta 1 minus B1 plus beta 2 minus B2 times X0 plus E0. And this is random variable, this is random variable, this is random variable. So this F is a random variable. And moreover, it's actually, this forecast error is actually normally distributed. So let's calculate its mean and variance. So taking expectation, so now we are conditioned on X. X is X1, X2 until Xn is the whole data, the vector of X. Okay, and remember our X0 might or might not be in this X. So condition on this X, that because we have this data, right? We can take expectation on both sides, and these terms should be equal to 0 because B1 is unbiased estimate of beta 1. Similarly, B2 is unbiased estimator of beta 2. So these terms will be 0 as well. We can pull this X0 out, okay, because of independency. And third terms, the E0 expected value of E0 conditional X, which is 0 because E0 is not correlated with X. So now this expected forecast error is 0. So this says that our predictors, least squares predictors, Y hat 0 is an unbiased predictors. Moreover, under the assumptions SR 1 to 5, we can actually show that Y hat 0 is the best linear unbiased predictors. Alright, let's calculate the variance. So I'm going to give you this formula variance. The algebraic computation is a little heavy, so we won't cover it. So look at this formula. We see that this variance of forecast error actually depends on 4 factors. First, depends on sigma square, which, remember what is sigma square? It is the variance of the random errors, random disturbance. So the higher of this variance, the higher our forecast errors variance. Okay, which makes sense, right? Because our sample has a lot of noise in it, so our forecast error should not be surprising. It should not be surprising that it's going to be big. Second, it depends on sample size. The higher the sample size, the lower the variance of forecast errors. Well, the more sample size, the more information we have, so we can make our prediction more accurate in a sense. Thirdly, is this variation in the explanatory variables. This is sum of deviation from the sample means. Okay. So the higher these variations, then in a loose sense that our data contain more information, so that make our forecast more accurate in a sense. Okay, let's set factor. Fourth factors. The value of the deviation of x0 from the sample average. The further away of x0 from the sample average, the higher the variance. And again, intuitively, if x0 is far away, very, very far away from our sample average, then loosely speaking, we have fewer information we can use to do the forecast. That results in a bigger, less precise forecast in a sense. Okay, however, we do not know that is sigma square, but we can estimate it as this. This is just we predict the residuals from the least square estimation. Square them add up divided by n-2. And I hope now you understand, appreciate that why we divided by n-2 rather than n. So we get this sigma hat square, estimate of sigma square, plug this one into the formula of this variance of forecast errors. We get this. So now that's sigma hat square. Square root it, we got the standard error, which is the estimate of standard deviation of the forecast. Right, we know that the sampling distribution of F is normally distributed because B1 is normally distributed, B2 is normally distributed, E0 is normal distribution. Okay, so we can standardize it. Take away mean divided by the standard deviation, we get the, let's call it Z, which is standard normally distributed. The normal distribution with mean 0, variance 1. Okay, so now replace the unknown variance of F with its estimate. Now we get a quantity T, let's call it T, which is no longer standard normally distributed. Instead, it's a T distribution with degree of freedom n-2. All right, so now we are ready to compute the prediction interval. So previously we have this y0 hat. That's a point predictor. Okay, so now let's compute the prediction intervals. So what is a prediction interval? It's a range of values in which the unknown value of y is likely to be located. Okay, here are the steps. Step 1, let's set the alpha. Typically, we want alpha to be 5%. Then calculate critical value, which is 100 times 1 minus alpha over 2 percentile from the T distribution. So remember that T distribution is quite similar to the normal distribution. It also has a bell shape. So this is TC, this is minus TC, and we want on this two shaded area to be 2.5% here, 2.5% here. So it adds up to 5%. That's the alpha we choose. Then we can calculate the associated prediction interval as this. And now I hope you appreciate that this is very similar to the interval estimation, very similar to how we compute the confidence intervals. Right, so this is a graph of these prediction intervals. So the solid line is the regression line, y hat 0, which is b1 plus b2 times x0. Okay, and this regression line pass through the sample average, x bar, y bar. Okay, and these two dashed curves is the prediction interval, the upper bound and lower bound of the prediction intervals. One thing you want to observe that is not kind of the width of the band change at different value x0, and this is because of the further away of x0 from the sample average, the higher value this is, and that results in a higher forecast, higher variance for forecast error. So we get a higher band. All right. Okay. Now let's look at the food expenditure model that we studied previously. And remember, we have all this information. So that's our B1, this is B2, and sample size is 40. We predict residuals, compute the sum of square residual divided by 40 minus 2, 38. Then we get the estimate of sigma hat square, which is 8,013.2941. Okay, now we want to predict the food expenditure of a household with weekly income of $2,000, which means x0 is 20. Remember, x0, the unit x0 is $100, so it's 20. Right, the individual prediction for y0 is easy to compute. Just b1 plus b2 times x0, which is $287.6089. And we can estimate the variance forecast error using the formula of this. We have an estimate of this. We know the sample size is 40. We know the average of x and deviation and total variation in x. So plug all this number in, we get this variance. Square root, we get this standard error of the forecast. Okay, now let's select alpha to be 5%. Find the critical value, which is this is TC is 2.0244, negative 2.0244. So compute the associate prediction intervals. So that's our 95% prediction intervals. This interval suggests that a household with $2,000 of weekly income will spend somewhere between $1,004.1323 to $471.0854 on food. And notice that this interval is quite wide, okay? Which means that our point prediction of $287.6089 is not too reliable. So why this is the case? One reason is that it's likely that we are missing other important factors, explanatory variables. So in our regression model here is simple. We only have one explanatory variables, one x, which is income. In addition to it, of course, income is one important factor that affects the food expenditure, but there could be other factors, and that might be missing. We might be missing that results in our prediction intervals to be wide. So, and next week we will do multiple regression models, okay, include more than one explanatory variables. Right, so our point individual predictions is y hat 0 is equal to b1 plus b2 x 0. Sometimes we might be interested in mean prediction. So remember, y0 is equal to beta 1 plus beta 2 x 0 plus e0, right? So this is a random variable because e0 is a random variable. So we might be, rather than the individual prediction, we might be interested in the mean prediction, which take expectation on the both sides. We get a beta 1 plus beta 2 x 0, and expected value of e0 is 0, right? And then a predictor, a natural predictor, is let's replace this beta 1, beta 2 unobserved parameters with our OLS estimate, is this. And you observe that this is actually the same as y hat 0, the individual prediction. However, the variance of the mean prediction errors is different from the variance of individual prediction errors. Okay, this is all I want to talk about the predictions.